test on Monday. Okay? So don't forget over the weekend to practice problems and stuff. We'll do some review here. So let's just start out pretty easy. How many electrons are there? In the universe? No, just kidding. Are there in a charge of 4.5 times 10 to the minus 14 coulombs. Well, he's an old rap star. So you might say, well, Mr. Ring, not many, because that's a pretty small number, right? However, charge of an electron is small, right? What is the charge of an electron, Lorena? Oh, yeah, you're right. Right, so each electron has a charge of 1.6 times 10 to the negative 19. We want to know how many electrons are in this many coulombs, right? So we just do a conversion like this. Now, you could do what Lorena just said. We could have 1.6 times 10 to the minus 19 coulombs down here, right? And electrons on top. Or what's another way to do it? Right, you could say, well, this is how many electrons there are in 1 coulomb. You could do it like that. Right, Mary? So remember, pay attention now so you do well later. 4.5 e to the minus 14 times 6.25 e to the 18, 281,250 electrons. Right? So you could also look at, you could say, well, what if we had a number of electrons? Say, what is a charge in coulombs? Well, let's use something different than electrons, of 38 protons. How would I do that? Well, Will thinks that the charge of a proton is in magnitude the same as the charge of an electron. Is he right? Yeah, right? They're just opposite. So 38p, but 1p is 1.6 times 10 to the minus 19 coulombs. So 38 times 1.6 e to the minus 19, 6.08 times 10 to the negative 18 coulombs. Is that clear? So just so you don't get confused with it, it doesn't matter which conversion factor you use. Like here I could just say, I could use this one here again. Oops. right? That's how many proton charges are in a coulomb. And then you would just divide by that, and you'd get the same number. Mhm. Let's look at some force problems. Well, if we have two charges and we're talking about force, what's our equation? If we're talking about the force between charges, what do we do? She just cut you off. Well, he started answering. He was just trying to give a nice quiet answer when you just yelled it in yours. KQ r over r squared, right? So if it says between a proton and an electron that are 3 nanometers apart. All right, so what do I do here, Tommy? Yeah. Since the proton's positive, it's going to be an attractive force, isn't it? Equal and opposite, right? An attractive force. The separation distance is 3 nanometers. What is 3 nanometers in meters? Negative 9. And then, of course, the charge on these electrons and protons. Oh, wait a minute. I didn't say what type of force. I should have said what is the electrical force. That's how I'm going to answer this. Because you could have, there's a gravitational force too, right? So, right, that's true. So Fe is K Q1 times Q2 over R squared, right? What's K? What's the value? 99 newtons times meters. It's positive 9. Okay, now some of you made that mistake on your packet. You used negative 9. It's positive 9, right? What's the charge on a proton? What's the charge on an electron? Magnitude the same. We took care of the direction, but the negative and the positive gave us the direction of these forces, that they were attractive, right? And then divided by r squared. Don't forget to square it. Oh. 99 times 1.6 e to the minus 19 times 1.6 e to the minus 19. Oh, I could have squared that, right? Divided by 3 e to the minus 9 squared. And the electrical force is 2.56 times 10 to the minus 11 newtons. How about gravitationally? Yes. Yeah, charge. Well, a proton's a lot more massive and than electron, and they have opposite charges, meaning that they're attracted towards each other. So if we did the gravitational force between a proton and electron, then is that an attractive force or a repulsive force? The gravitational force between a proton and electron. It's also attractive because it's always attractive for gravity. Whereas electrical force has a couple of flavors, right? Strawberry and banana, or something like that. Now the G is a lot smaller, but the constant's a lot smaller, and it's named G. And the mass of an electron, who knows the mass? Are you talking about physics? Oops, what does that mean? Yeah. Don't ask about the visual right now. When I'm reviewing for your test, it's coming up. What's the mass of a proton? And the R would be the same. Okay. 6.67 e to the minus 11 times 9.1 e to the minus 31 times 1.6 e to the minus 27. That's a small number. Divided by 3e to the minus 9 squared. That's still a small number. 1.08 times 10 to the minus 50 newtons. It's much smaller than the electrical force. Well, they're held together with nuclear forces. And you're going to learn, well, maybe you learn about them, but for everybody, have you taken chemistry? So you probably learned about nuclear forces in chemistry. But you'll learn about, like we have magnetic force, electrical force, gravitational force. There's also nuclear forces, van der Waals forces, all those forces that are in play within nucleuses of atoms, and, and between molecules too. There's molecular forces. Well, some of it we don't get that way because the forces come about from actually being in contact with each other. So yeah, so they have to be in so that it doesn't get calculated the same way. I couldn't give you a formula for it though. Somebody could. Okay. Oh, let's talk more about these electrical forces in terms of like, let's take a 2 Coulomb charge, just to make things easy, and a 4 Coulomb charge. This is sort of just working off the old question, okay? And let's say it's separated by 4 meters. This would have a force associated with it, right? And I could calculate it, right? And let's say it gives me the force F. And it would be a repulsive force because they're both positive. Now, what would happen to the force if I cut the distance in half? Okay, so that's the first question we should ask. Does it get bigger or smaller? Stronger, yes. And therefore, since it's an inverse squared relationship with the distance of separation, we know it's going to be, what's 1/2 squared? So it's going to be 4 times that, because a quarter on the bottom is a 4 on top, right? You remember that on your SATs. Lines, yeah, because lines like that help. You have to remember when you get stuff like a quarter on the bottom is a 4 on top, so you can be quick with them, you know? I heard, yeah. Now they'll just go around with a little stick, and they just plug it in, and beep, and they'll look and say, okay, here's your intelligence, here's how little you worked, and here's your success rate in college. Huh? It would be, wouldn't it? Of course, that would assume that, you know, that people stay the same and we're already, everything's set in stone, right? You think everything's set in stone? Who? It's true. Well, I'm not surprised Annika did well on her SATs. No. So, at any rate, what would happen if we double the distance r? Does it get bigger or smaller, the force? That one gets smaller. 1/4 r, or 1/4. Because you got to square it. Yeah. There's a number of questions like this on the test. They're hidden in multiple choice. Multiple choice, moderate, hard. Stuff like this. No, it says like this, like take an electron, twist it around, spin it to the left, take it to the right, add a proton. How's the force? 1/9, 1/16, or 1/32 of the original value? Twice, of course, yes. Wait, what? Yes. Yeah, so if we took this, instead of just working with 2, because that can be confusing, if now we went to a third of R, does it get bigger or smaller? A bigger force, and it's 1/3, square 1/3. 9. Right? It's important to pay attention because these, then when you miss 3 multiple choices in a row on this stuff, don't come complaining to me. Well, you can complain, but just realize. Right. Yes. Okay. What's the force does an isolated point charge of 2 coulombs exert within or from a electric field of 600 Newton coulombs? Right, so the electric field was defined as the force on a point charge, the force per unit point charge like that. So Fe is the electric field times Q, which would be 600 nanocoulombs times 2 coulombs, or 1,200 newtons. So that's what that charge would feel in that electric field, okay? So that's the force that would be exerted on it. How about, we'll call this B. What is the electric field around a 2 coulomb charge at a distance of 2 meters from the charge? How do we get that one? E equals kq over r squared, where k is 9 times 10 to the 9. Q is the charge. $18. 3, 6, 9, 4.5 times 10 to the 9. What's my units? Newton per coulomb. It comes about with the fact that electric field is force times charge, right? So if we look at what the electric field strength would be around an isolated charge, then we have force times that charge, so that one of the charges drops out. So let's look at the Q on it, the 1Q value, the big one. All right. Tomorrow, I could do one with them too, maybe. I could do a problem with them that I don't do with you. See, with them, I do more problems because I don't have to yell at Mary so much. Just kidding, of course. I know whose fault it is. Hannah's not around for her to be corrupted. So you're taking the role of Hannah today. Sam, be careful. I'm just kidding around. Okay, number 4. How much energy does an electron gain in moving through a potential difference of 400 volts? So what gives us potential difference in like everyday life? Potential difference is what? No. Well, it's energy per charge unit. But like a battery, 1-volt battery. So it's the voltage, right? So we have to get charge separation to create voltage. Okay? And an electric field is set up. So if you have like a voltage, another formula for electric field is voltage that's separated over a distance. Okay, so a battery is really like where you have 2 plates separated over a distance, okay, with an amount of charge. The different thing with a battery, though, is that every time the charge goes around the circuit, chemicals in the battery will take it, put it back, that charge back on the plate. So that's why it keeps running until the chemicals die out and you need a new battery. So this is voltage. Everyday life, it's batteries or it's in our wall sockets created from charge separation at a power plant. Right? So how much energy does an electron? So Q, if you get confused, it's always good to like write the charge, the stuff that you're given. We know an electron. And you say potential difference is voltage, so V is 400. And it says how much energy, so we're looking for that UE. And do you have a formula that relates potential energy to voltage and charge? Right. Okay, so the voltage is defined as how much potential energy per unit charge. Okay? So UE is VQ. Did I do that right? So the voltage of 400 volts, or it's also a joule per coulomb, a volt is, and an electron of 1.6 times 10 to the minus 19 coulombs is 400 times 1.6 e to the minus 19, or 6.4 times 10 to the minus 17 joules. Okay. So that's how much potential energy it gained. Now let's say it's released back. How fast will it go when it gets back to its original location? the initial energy, I don't even want to use that because you confuse the E with the electric field. So UE just ends up becoming K. And K, what's the formula for K? And UE was 6.4 times 10 to the minus 17 joules. Well, what's the mass of an electron? 17. Whoops. (9.1 times 10 to the minus 31 kilograms V squared. So, well, 6.4 times 10 to the minus 17 times 2 divided by 9.1 e to the minus 31 gives us that. Square root it. V equals 367, 1.2 times 10 to the 7 meters per second. So if you're asked for like speed or velocity of a particle or an electron or a proton, well, first off, you got to remember that energy is probably a conservation of energy where it's becoming kinetic, right? And then you have to remember, well, I have the masses of the protons and the masses of the electrons. They're on my reference table, where electrons 9.1 times 10 to the minus 13, and the proton is 1.6 times 10 to the minus 27, right? This is the velocity when it gets back. Yeah, as it accelerated back. So the work was done on it as it moved through the electric field, right? And that work that was done on it can be converted back into kinetic energy, 1/2 mv squared. And so this would be the speed when it went back to its starting point. You're lucky I don't have a meter stick. Numero 5. Oh, number 5. How many extra electrons? Must the 40 kilogram object have to levitate in the 10,000 volt per meter? Because remember, electric fields can be measured in voltmeters as well. That setting up a consistent electric field between two parallel plates, okay, with a certain voltage separated by a certain distance. So 40 kilograms would be like, well, probably Mary, you might be about 40 kilograms. And this is a strong electric field, so we wouldn't have to give too many electrons to you to get you to levitate. Well, she would be, with the extra electrons, no, but sparking, you'd be all right. would put her in a suit. I just picked her because it's 40 kilograms. You look like the smallest in the class right now. I should have, you're right. Okay, so we have this giant electrical field set up, okay? And we have an FE force up and an FG force down on the levitating thing, okay? And so FE ends up equaling FG, but FE is EQ and FG is mg. So the first thing we're going to do is find out what this Q is, because if we have this Q, then we can solve for the number of extra electrons from the charge. So the mass is 40 kilograms, G is 9.8, and E is 10,000. A voltmeter is also a joule coulomb, so we'll be left with joule or coulombs. So Q is 0.0392 coulombs. Okay? And then we can convert that to electrons. What am I going to use as a conversion factor? Okay, that makes sense. .45 times 10 to the 17 electrons. What do you think, Mary? Can you handle that electricity? Perfect timing.